Welcome to this podcast from the Triple Helix Cambridge February Café Scientifique event, sponsored by the Medical Research Council. I'm Mira Senthilingam from thenakedscientist.com. Each month, the Triple Helix Society in Cambridge hosts a free event at the ADC Theatre in Cambridge, looking into a variety of scientific issues and allowing you to put your questions to the scientists involved. This month's Café Scientifique investigated our place in the cosmos. And so to find out just what our place is in the vast expanse that is our universe, I spoke to the event speaker, Dr. Caroline Crawford, from the Institute of Astronomy at the University of Cambridge.
I was trying to put our place in the universe into some kind of context. We're very familiar with the Earth, but how does the Earth and the solar system fit into our Milky Way galaxy? And then how does our Milky Way galaxy fit into the whole larger scale structure of the universe? So it's a question of looking at scales of things, we're looking at numbers of things, and trying to just map out the local geography of our universe, what we understand and what we know.
So what is our place in the cosmos, which was the theme of the talk? So we're here on Earth. Could you just take us out from Earth and out into the rest of the universe?
Well, we start with our Earth, which is just really one of 8 planets that orbit around our Sun, and the Sun is just a very average star within our galaxy. But our solar system stretches perhaps out to about a light year in diameter, and a light year is a distance of 9.5 million kilometres. However, that is tiny compared, that's only about a quarter of the distance out to the nearest star. So you've got to get this sense of our own star and its solar system being a tiny pocket surrounded by lots of space, and then long distances away you have other stars that are all part of our Milky Way galaxies, like this giant spinning frisbee in space. And altogether about 100,000 million stars within our galaxy, all held together. I was very much sort of building up that gradual picture, starting from our solar system out to our environments, looking at the stars, the gas, the dust, the matter within our Milky Way, how it's distributed, and how that comprises the Milky Way, but then how the Milky Way itself is situated within the local group of about 40 galaxies, and how that's right on the edge of a larger cluster of galaxies, and then spanning out to the much larger scale distribution of those galaxies and the clusters of clusters within our universe. So taking it right out to the biggest scale we've been able to observe.
And how far have we been able to observe of our universe so far? So how far out do we actually know about?
Well, you can turn the question around and say, how far back in time we can observe in our universe? Because, of course, the furthest things we're looking at, we're also seeing them as they were much earlier. And certainly in visible light, we can see back to galaxies that are perhaps within, say, 500 million years of when the Big Bang happened. It sounds a huge time. That's still relatively early on within the history of our universe. And that's probably as far back as we've been able to get in the optical waveband so far. And
how are you able to actually work that out?
Obviously, it's difficult when you're looking at very faint objects, but we do have a way of measuring distances which is called redshift. So if something's moving away from you, and if it's far away, it's across the universe is expanding. The further away something is, the faster it's moving away from you. So you have this clear relationship between the two. That's a way of getting a handle on how far away something is from us. And so you collect the light from the distant object. You compare it to the light of nearby objects, which is tricky because obviously the galaxies have changed and evolved, and they've turned into different types of galaxies. But with a bit of guesswork, you can work out how much the spectrum has shifted as related to how far away the galaxy is.
One thing you were trying to stress this evening is the sheer scale of things. So when you're talking about hundreds of thousands of kilometres and light years, it's hard to even get your head around such numbers. What's a good way for people to just understand just how distant our planets and then our stars and then our galaxies really are out there?
It's difficult to find analogies as such because the problem is the distances grow very quickly, and so we have to think of it in terms of multiples of something. It's where you grow distances not by adding stuff but by multiplying stuff. So you might say distance out to Pluto is about the order of 40 times the distance from the Sun out to the Earth. And then maybe out to the edge of the solar system, it's about 40,000 times the distance between the Sun and the Earth. But again, you start running up into big numbers, and maybe you choose a new unit and you say, okay, well, if that's the whole size of the solar system, maybe you need 4 of those to get to the nearest star. And you start, again, you have to keep talking in multiples the whole time because things grow exponentially.
In terms of our universe, how much of it do we actually know about? It's a very small percentage that we actually know of so far.
Well, I wouldn't say it's a small percentage we know of. There is a very small percentage that we can actually visibly see, or see in any wave band, and we reckon that's less than 5% of the universe actually emits radiation of any colour. So you're talking right down to radio, infrared, up to ultraviolet, X-ray and gamma rays. There's a huge tranche of matter which we know is there because we can feel its gravitational pull. It doesn't emit light at any wave band, and that's called dark matter. And then beyond that, in terms of the components of the universe, there's probably about 3/4 of the universe which is termed what we call dark energy, and that's an even more unknown quantity. And that is, again, we can infer its effect on surrounding objects, not this time by gravitational pull, but by a new force which causes a push and is actually accelerating the expansion of the universe. But again, that's a huge chunk of the universe, but it's even more unquantifiable than the stuff we can't see.
How old is our universe thought to be, and how was it thought to have been created?
Our universe, we reckon, is about 13.7 billion years old. That's a fairly good estimate. And again, that's mapping the velocities of structures and using galaxies and clusters of galaxies, if you like, as tracer particles, mapping the flow of the universe outward and then extrapolating that back. You know, if things are moving at that speed, accelerating that speed, how long would it take for the universe to get as big as it is? So that's how we get this idea of the age of the universe.
And so knowing the age, how was it thought that the universe formed in the first place?
Well, if you extrapolate this expansion of the universe back and you wind time backwards, you know, obviously 100 years ago it was smaller than it is now. You wind back 13.7 billion years ago and you find the universe compresses down to all that matter, all that material within almost like a point. So this whole expansion of the universe, it was discovered by Edwin Hubble in the 1920s. That's one of the first key evidences for this idea of a Big Bang creation point to the whole universe. And it's just from tracking back the expansion of the universe.
Now, another thing you stressed was that there's a lot we still don't know. What would you say the more immediate kind of challenges are then facing this particular field of astronomy?
There are so many challenges facing astronomers. You can start with the fairly local problem is we're now discovering planets around other stars. We've yet to discover anything that looks like an Earth-like planet. It's quite hard because these are the smallest, they're the dimmest, they take longest to go around their star. They're going to be the hardest to track. Now, we think that's going to be a discovery in the next few years. That will be very exciting because that tells you a lot about possible habitats for carbon-based life forms within our galaxy. Of course, there's a lot of work going on within the particle physics domain that ties into understanding the nature of dark matter and dark energy. And it could be, again, on the timescale of the next few decades, we're going to make huge strides in our understanding that then feed back into understanding the astrophysics. So these are the major challenges that I can see that astronomers are facing.
Dr. Carolyn Crawford from the Institute of Astronomy at the University of Cambridge, giving us just a brief introduction to the wonders of our universe. But as you can see, the sheer scale of our solar system and our galaxies can be hard to get your head around. And there's also still a lot to find out about what's out there in the universe and beyond. But remember, the main aim of Café Scientifique is to help the residents of Cambridge understand more about the topic at hand. And this month was a packed event. So after Carolyn's talk, there was a chance for audience members to get their questions on the topic answered.
You spoke about those rocks, asteroids, is that what they're called?
Asteroids, yes.
And amongst all that, those stars, what part are they playing? Don't they bump into things? And
It's a very good question. So this is about the asteroids that I showed you that I said were part of our solar system. We only see them by the reflected light of our sun. Now, they're inherently part of a planetary system. We think all those asteroids, they would have made a planet between, say, Mars and Jupiter, but you've got the effect of Jupiter's gravity. It stirred them up. It stopped them from collapsing down under their gravity to form a planet. So if you like, they're the debris. The rocks that are further out in the Kuiper Belt, the rocks that are in the inner solar system, they're all parts of stuff that's left over when the planet's formed. In terms of the global scale of the galaxy, they will be only found around stars. Yes, they might be colliding with each other, but they're part of planetary systems, and they form from those little nebulae that collapse around the stars. And so they're intrinsically always, we think, part of a planetary system.
With these galaxies, they seem to cluster, assemble. due to gravity. However, you saw many different voids between the various different clusters of galaxies. Seem to be a more periodic arrangement. Do you know why they form these arrangements? Is there any kind of structure that's making them form it, or any system that's making them form it, or do we simply not know?
The challenge for cosmologists is if you start off with a fairly uniform universe that has expanded from the Big Bang before any matter condenses, it starts clumping together, forming galaxies. Galaxies start merging together to form clusters and bigger galaxies. How do you end up with a universe that looks like today? There are simulations that try and mock this up. You have one part of the dense universe that's slightly overdense. It's got slightly more gravity, slightly more mass. It acts as a kind of focus for stuff to condense around it. Now, what we find is that you have these filaments, and matter seems to fall along the filaments, and the clusters form at the nodes where the filaments cross. So we have simulations, again, if you Google something called the Millennium Simulation, that's the best example, where we think matter sort of gets funneled along these filaments, it gets poured along these directions, and it gets concentrated within them, leaving the voids open and devoid of the matter. So it is a huge problem.
But you also said that the dimmer galaxies take longer to arrive to the Hubble telescope. However, the more brighter take shorter time to arrive. Yeah. When you see this cluster of galaxies, how do you know that they're simply not a large arrangement, or say 40% galaxies that are really far away that are dimmer than others? And how do you know they're really clusters?
Colours. Galaxies at the same age will have approximately the same colours. The other thing was I can measure the redshift. Okay. The redshift is related to the distance. People go out and they take redshifts of every single object and work out which ones are in the cluster. But the canniest thing is that I don't use optical, I use X-ray astronomy. If I look at a cluster of galaxies in X-rays, I don't see the individual galaxies. I see what's known as the intercluster medium, which is a hot X-ray atmosphere that fills it. It means I know there's a cluster there. We can actually measure distances and colours of individual galaxies and the whole cluster as an entity, and that helps us.
Is the structure of the universe, has it been, as it were, quite stable since quite near the Big Bang then? Are there the same sort of structures of galaxies, superclusters and everything that we're seeing repeating over and over?
We think it's a hierarchical process. You start with very small structures that have merged together to form galaxies. Galaxies merge to form bigger galaxies. They come to form clusters. And so you have a progression as the universe evolves. When you look in the infrared and the optical at these very distant galaxies, the ones I said you can't really see very well in this image, you look in the infrared, you can see them in more detail. They look blobby. They call them Lego galaxies. Okay, the idea of assembly, lots of little bits building a galaxy. Again, you don't see those first components being formed, but you see those components come together and forming the first galaxies. So you do see an evolution of structure, and certainly the richest galaxies, clusters of galaxies, like I showed you, like this one, are a relatively recent phenomena, which is probably like in the last billion or so years, few billion years of the universe. We think the universe is of the order of 13, 14 billion years old. So there is a progression and evolution of growth of structure within that time.
As you said that the space is expanding, I'm just wondering, do we have any idea of what's outside the space?
No. As you can see, there we have an observable horizon. We can only observe so far, whatever is 15 billion light years away. There's stuff outside that horizon which exists, which is still part of our universe and we can't see. What is beyond that, and what is even beyond our own universe, we don't even have the concept of stuff that exists outside our universe. It's like the same question, what existed before our universe? We have no idea. We say all time started at the start point of our universe. We don't have words to describe it. So at that point, what's outside the universe, what's before the universe, are there other universes, are there multi-universes? There are very serious scientists who tackle that problem, but they will do it as a thought experiment. It'll be pure mathematicians, and a point where the pure mathematics crosses almost into philosophy, the combination of the two. They are not things that we expect to be able to prove one way or the other in the near future.
But the asteroids and their irregular shapes, isn't there a theory that they were planets or planetoids at one point and then got torn up by tidal effects.
So there was a theory that there used to be a planet between Mars and Jupiter. So I'm sorry to say this, but maybe 20, 30 years ago, if you read in a book, they would tell you there was a planet that got destroyed by gravitational tidal forces. The thinking has changed over the period, and we think that those tidal forces acted to stop them congregating under gravity. The reason they're shaped like potatoes and misshapen is because, or the majority of them are, is because they're small. They're about, on average, tens of kilometres across. The biggest asteroids series, I think, is now classed as a dwarf planet. It's of the order of about 1,000 kilometres across. If something is rocky and metal and it's 1,000 kilometres across, it's got enough gravity to pull it into a spheroid. If it's only about tens of kilometres across, it doesn't form that ball shape. Okay, so they're misshapen because they've had lots of collisions in the past, and also they don't have enough mass to make the gravity important to pulling them around. They haven't gone through any sort of geological processing. They haven't been molten at any stage. They haven't got deformed in that way. So they have a very different geological history to the objects that are round, and it's to do a lot with their mass. Okay, so partly it's collisions, but it's partly their mass and their size.
Could you say something perhaps about dark matter and what's going on with that?
Somebody very astute at the back has pointed out that I've only talked about 4% of the universe, and only probably about 10% or so of our observable universe. We have all the things I'm showing you here are glowing, are producing their own radiation. It's all matter. We think, what we call normal matter, baryonic matter, that produces light because it's hot. And if it's cooler, it produces infrared light or radio light. If it's very hot, it produces X-ray light. So it produces light at all colours of the spectrum, not just the visible. However, there is a whole class of matter, probably about at least 10 times more than the stuff that we see, that is there, but it doesn't produce light in any waveband, and that's the dark matter. We know it's there because we feel its gravitational pull. If you look at a spiral galaxy like Andromeda, and it's spinning, I've told you it's spinning, what you can do is measure the velocities of these stars. The motion is because they're responding to the gravity within that orbit. However, the problem is when you look at our own spiral galaxy, when you look at all these spiral galaxies, these stars right out on the edge and way beyond this plot are travelling too fast. They shouldn't stay bound to the galaxy. They should just fly off into space. The fact they stay bound means that there is more matter there than what you actually see. And this is the dark matter. And if you map all the velocities of these stars, you say, okay, they're responding to a gravitational potential. Where is the mass they're responding to? You find it's this ginormous halo outside of this galaxy, not necessarily in a disk shape, but way beyond the disk, maybe more spherical. Recent results a few months ago suggested more kind of beach ball shaped. A kind of misshapen ball of dark matter, most of it outside our galaxy. The question is, of course, what it is. There's a lot more of it. It could be some kind of baryonic matter that doesn't produce light. It can't just be things that are cold, like brown dwarfs or Jupiters, because they're producing infrared light. They're not producing light at any waveband. The current thinking is that it could be some kind of exotic particle, something that we haven't yet discovered, something that's still challenging our theories of particle physics. And this is where you get to the whole field of astroparticle physics, where what happens about our understanding of tiny particles can influence perhaps mass on the larger scale. So dark matter is a huge uncertainty. It is a huge enigma.
What about dark energy then?
Uh-huh. So those of you that were doing the maths when I said I was only showing you 4% of the visible universe, and here I'm saying, well, the dark matter is 10 times as much as the optical matter, might have worked out there was this huge gap of stuff I wasn't talking about, and that's the dark energy. We know even less about that. I've read a lovely analogy, which is you have to imagine that you're out in the ocean at night. So the stuff we can see is the lights on top of the masts of all the ships. The ships that maybe you can tell they're there because the way that the mast with the light on is moving, there's a ship underneath. That's the dark matter. And then the whole of the ocean is the dark energy. And we know even less about that than we do about the dark matter. And we didn't know about it at all, really, for sure, until about 10 years ago. And the problem is this expanding universe. We expect the universe to be expanding, like so from the Big Bang. The universe expands out depending on how much energy is released and also how much stuff there is in the universe. There's a lot of stuff we'd expect at some point gravity to win and pull it back. There isn't a lot of stuff you'd expect the universe to carry on expanding as normal. Now, when I started doing research in the 80s, people were trying to measure when it stopped and when it turned round as a way of measuring the mass in the universe. What was discovered 10 years ago is the universe is neither decelerating or just expanding. It's actually expanding faster and faster and faster. In order for this to happen, you have to say there's some extra force. We call it dark energy because we don't know what it is. Don't think the name dark energy means there's energy out there. It just means it's dark, it's got something to do with force and energy, and we don't know what else to call it. You could get 3 different astronomers up here and they'll give you 3 different ideas of what it is. But what we do know about dark energy is it's tied to an absence of space. We're familiar with gravity. If you remember gravity is tied to matter. The more mass you have, the more gravitational pull you feel. The closer you are to something, the more gravitational pull it has in you. Dark energy is tied to the spaces between the galaxies. So again, this is how weird it is. We have a force that is tied to an absence of stuff. The wider the void, the more dark energy there is. And where gravity is a pull, dark energy is a push. And so in the early universe, galaxies are close enough together that gravity's dominant on the small scale. They start congregating to build clusters and things. Meanwhile, the whole universe is expanding. At some point, the distances between the galaxies and the clusters gets big enough that the force of the dark energy in the voids becomes important. It starts pushing the universe further and further apart. I mean, I said this is getting very esoteric. This is stuff that we didn't know about 10 years ago, and yet we think if you weigh up all the matter energy density within the whole universe, this accounts for about 3/4 of it. And we have even less idea of what it is than we do about dark matter.
Carolyn, do you think we're alone in the cosmos after studying the stars for so long?
I don't think we are. I've told you there are 100,000 stars within our galaxy, 120 billion galaxies in the universe. There are certainly plenty of other planets. We may or not have discovered Earth-like planets yet, but we imagine there are hundreds, thousands, millions within our own galaxy. They're difficult to find because they're small, they're far away from the stars, they're dim. So there are lots of places where life could have established itself. And certainly I would be very surprised if we were on our own. If you look through the universe, you look in these clouds of gas, they have molecules that are carbon-based. There are some silicon-based molecules, but it's quite likely that other carbon-based life forms could be out there. If there are other Earths, lots of carbon, the sort of organic chemistry, it could have arisen. The question is, well, a couple of questions. One, would they be at the same time as us? It's taken, 13 billion years or more for us to have become sentient, have evolved into intelligent civilization. Other civilizations maybe have peaked into intelligence way before us, or maybe they're still at the microbe stage. You get all these generations of star formation and star growth, and the planets and the evolution of life takes billions of years. The other thing is, remember the distances I've talked about. Nearest star, 4 light years away. A round-trip conversation by sending signals out, we beam them out to the star, that would take 8 years. You start looking at some of the nearest stars that have planets on that's within 150 light years. You start getting to the unimaginable scales that even to have conversations, let alone we can't travel at the speed of light, we can't send our spacecraft out there yet. I think the possibility of contact is very unlikely. So ways we might detect it, we have already got to the point where we can detect molecules in the atmospheres of other planets. Big gas giants like Jupiter is really close into the sun. There are some planets where we're discovering methane within the atmosphere. That could be a signal of life. So it could be that it could be geological as well. That may be the way that we would show whether there was life or potential of life on other planets. Say we discover Earth-like planets, say we discover something like methane in their atmosphere, but that's still a very long way from actually discovering life. It is certainly one of the things that drives a lot of people within this science. I have a lot of colleagues within my department who are looking for exoplanets. The search is on to find the first Earth-like planets out there. And of course the question at the back of everyone's minds, how unusual is the Earth? How unusual are we? So if you ask me personally, I don't think we're alone, but whether we'll ever know it is another matter.
So we may not be alone in our universe. A good range of insightful questions there. And I caught up with some of the audience members afterwards to find out just what they'd learnt.
I was expecting
Much like what Dr. Crawford gave, but the mixture of the slides she gave and the sort of density of information was a lot more. It's at a higher level than I imagined, which really suited me. I was very excited and thrilled with the whole thing.
Did it leave you phased at all about our place in this large universe?
Yeah. I think that's the right attitude.
A lot of it was somewhat familiar, but I was quite interested in the dark matter and the dark energy things, and I thought it was a good explanation actually, because I wasn't that clear about what was going on with it, and I thought it was good to have someone that's close to it to explain it, because it made sense of it to the extent that you can make sense of it.
So most people seem to have walked away in awe of the sheer scale of our universe, as well as gotten an insight into complex topics such as dark matter and dark energy. So a well-rounded event. Now, I also spoke to the event organiser, Kate Quinlan, to find out what we have to look forward to at next month's event.
OK, so next month we've got Dr Paul Fletcher from the Department of Psychiatry at the University of Cambridge speaking, and his presentation's entitled Jumping to Delusions, How the Brain Takes Dangerous Shortcuts. And so if you'd like to come along, that'll be at the ADC Theatre in the Larkham Studio on Wednesday the 24th of March at 7:30pm.
And you can find out more about that event online at cafescientifique.org/Cambridge. So come along in March to the ADC Theatre and join in to find out more about our brain's shortcuts. The Triple Helix Cambridge Café Scientifique is sponsored by the Medical Research Council, and this podcast was produced by me, Meera Senthilingam, from thenakedscientists.com.